All right, if you're aiming to become an embedded engineer, you know that the board support package interview can feel, well, pretty intimidating. So today, we're going to crack that code. We are going to demystify the core questions you're almost guaranteed to face and give you the mental framework to absolutely nail it. Let's get right into it.
We're going to structure this as a story, the journey of bringing a brand new board to life. We'll start with the foundational concepts, then we'll look at the blueprint for describing the hardware to the software. After that, we'll see the spark of life during the boot sequence, peek inside the OS kernel, and finally, we'll get our hands dirty with some real-world troubleshooting.
So, first up, Section 1, the foundation. You can't build a house without understanding what a brick is, right? Same deal here. You've got to know these core terms before you can build anything.
Let's just start with the biggest question of them all, the one you will absolutely be asked. So, what is a board support package?
Okay, think of it like this. A BSP is the ultimate custom adapter. It's the crucial bridge that connects a generic operating system like Linux to a very specific piece of hardware. I love the analogy of a tailored suit. The OS is like a standard suit pattern, but the BSP is the master tailor who makes it fit your specific board perfectly, with all the right drivers and configurations to make it all just work.
These three terms get mixed up all the time, but they have really distinct jobs. Using the building analogy here, the firmware is the concrete foundation. It's the very first thing that gets going to prep the hardware. The operating system, or OS, is like the general building code for the city. It provides the rules and services for everyone. But the BSP? That's the detailed custom architectural plan that says exactly how those building codes will work on this specific foundation. They're a team, but they each have a very different role to play.
This is a super important concept in our world. See, regular compilation is easy. You write code on your laptop, you build it on your laptop, and you run it on your laptop. But our tiny little embedded boards, they just don't have the muscle to compile a whole Linux kernel. So what do? We cross-compile. We use our big, powerful laptop to build the software for a completely different kind of computer, like a small ARM board. The key takeaway is simple. We build it here so it can run over there.
So why is Linux pretty much the king of the embedded world? Well, it really boils down to two things: total control and a massive community. Because it's open source, you can literally see and change anything. You can strip it down to be super lightweight and efficient for a tiny device. And the community? That's your secret weapon. It means someone, somewhere, has probably already written a driver for your hardware, which can save you weeks of work.
All right, moving on to Section 2. Now that we've got our basic concepts down, we need a way to actually tell our generic software about our very unique hardware. We need a blueprint.
And that blueprint is called the device tree. This is a brilliant idea. See, in the old days, you had to hard code all the details about a board right into the Linux kernel source code. It was a mess. Now, we just pass the kernel a simple text file at boot time that describes everything: the CPU, the memory, which peripherals are at which address, everything. This is what allows a single, unchanged kernel to run on literally thousands of different hardware designs. It's an incredibly powerful concept.
Okay, so we've got our tools, we've got our blueprint. Now for the really exciting part. Section 3, the spark of life. What actually happens in those first few critical moments after you hit the power button? You can think of it like a four-person relay race. First, the boot ROM, which is burned right into the chip, wakes up and does a quick check before handing the baton to the bootloader. The bootloader, like U-boot, is more sophisticated. Its main job is to set up the memory and then load the big players, the Linux kernel and that device tree blueprint we just talked about. Once that's done, it passes the baton to the kernel, which kicks off the init process, the final runner that brings the system all the way to a login prompt.
And boom! The system is up and running. But for a BSP engineer, the job is just getting started. So welcome to Section 4, where we go inside the kernel. A huge part of your job is going to be managing, updating, and, well, fixing the very heart of the OS.
Let's talk about a core kernel concept: memory. You have your physical memory, the actual RAM chips on the board. But the kernel plays a clever trick. It gives every single program its own private, virtual memory space. This is a game changer because it acts like a safety bubble. It means one badly behaved app can't just reach out and mess with the memory of another app, which prevents the whole system from crashing. It's one of the key things that makes modern operating systems so stable.
All right, here's a classic interview question. An interviewer might say, okay, we have a product out in the field. We need to update its Linux kernel for security patches. How do you do it?
The key here is to show you have a methodical process. You don't just jump in. First, you read the release notes to see what's changed. Then you carefully reapply all your custom stuff, your patches, your configs, your device tree. Now, the trickiest part is usually updating your custom drivers, because kernel APIs can and do change. And finally, you test, and you test again, and then you test some more. You test everything.
So what happens when things go really, really wrong? I'm talking about the dreaded kernel panic. The whole system just locks up and dies. Your interviewer wants to know, what's your plan? How do you attack this problem?
The first rule of kernel panics is don't panic yourself. You investigate. Your number one clue is always the last thing the kernel printed out, the oops message on the console. That's your starting point. If you need to go deeper, you can set up tools like kdump to get a full memory autopsy report after a crash. And for the really tough bugs, you break out the big guns like a JTAB debugger to perform live surgery on the system. The goal is always the same: methodically hunt down and isolate the cause.
Okay, let's head into our final section, where the theory really hits the road. Section 5, tackling practical challenges. This is all about the day-to-day puzzle solving that you'll actually be doing on the job.
Here's a situation you'll see all the time. The board boots up, but the Wi-Fi doesn't work, or the screen is blank. The system says it can't find the right driver. What do?
You run down a checklist. No guessing. First, is the driver even built into your kernel? You check your kernel config. Second, did we tell the kernel about the hardware? You double-check your device tree, that blueprint. Third, are there any error messages? You check the kernel logs with a command like dmez. Seriously, following a systematic process like this will solve 99% of your driver problems. I love this quote because it's so true. It gets to the heart of what we call board bring-up. Long before you're even worrying about Linux drivers, you have to get the absolute fundamentals working in the bootloader. If your memory isn't stable or your CPU clocks are wrong, nothing else matters. It's like trying to build a house on a foundation of quicksand. Getting those first few low-level steps right is absolutely everything.
And just like that, we've done it. We've taken a journey all the way from a bare piece of hardware to a fully running system. We've covered the core concepts, we've mapped out the hardware with a blueprint, we've followed that spark of life through the boot process, and we've learned how to debug the system when it fights back.
So you now have the mental model for how this all fits together, which is the key to answering any BSP interview question. You don't just know the answers, you understand the story of the board. So the only question left is for you. Now that you know the what and the how, what amazing thing are you going to build first?